Okie dokie. So, it's a lot of talk of evolutionary algorithms. There will be even more in this. Putting these two talks together, back to back, has actually been quite a good example of convergent evolution. Because even though we're separated by a channel, Carsten and I seem to be coming up with a lot of very complementary ideas. Kindly, two of the ideas that he mentioned but didn't follow up on fully, I'm now going to talk about, which are calibration and the evolution of system geometries. So that's my title, This is what I'm going to walk you through today. So firstly, I think it's always important to believe that the person who's talking to you about AI knows something about AI, because in one of my roles as an independent scientific advisor for the Bridge AI scheme, what I learned is that a lot of small and medium AI companies don't actually seem to know that much about AI. I'm then going to talk about using artificial intelligence as a calibration and validation tool. I'm then going to talk about how we can expand that framework into not just optimizing the parameters of a simulation, but optimizing the simulation itself. And then if there's time, I'm going to wax lyrical a little bit. I'm going to say a few controversial statements and hopefully start an argument or two about artificial intelligence. So, part one, who am I? Why should you care what I've got to say? So a lot of my career is focused around discrete element method modeling. Indeed, my title is Professor of Digital Particle Technology. I've done several Royal Academy of Engineering fellowships focused around applying discrete element method and MPPIC models within industry. I've worked on industry-focused DEM projects with multiple different companies spanning multiple different sectors, and I had the privilege of leading a project with the International Fine Particle Research Institute, which was their first ever round robin, which I'll talk to you a bit more about in a few slides' time, trying to really find down what industry is doing in terms of calibration, what they're doing wrong, and what we can learn potentially from all the wrong things that they're doing. On the AI side, I do a lot of work with the Alan Turing Institute, with Bridge AI, as I've mentioned, and I'm also the deputy director of a supercomputer, so I get to see and process and rate lots of really interesting AI projects. So I've got a broad overview of the field, but in this talk I'm going to go very, very narrow and talk particularly about the discrete element method. So where did I start on this road? Well, as I said, I did this 6-year project with IFPRI, the aim of which was, as JP, I think it was, has pointed out very well, a lot of people are using DEM, but they are decidedly inexpert about it. They don't know what models to use. They don't know how to calibrate it. Some of the industries I've worked with don't even know what calibration is when I first speak to them. So we did what they called a round robin, and this was a new experiment for IFPRI. We had 11 multinational companies who used DEM, as well as some academic partners. And the idea was to look at what all of these people are doing, see what they're doing well, see what they're doing badly, and see if we can combine all of this information to create something close to a gold standard for DEM calibration. And I think for certain subsections of that, we've actually done a half-decent job. Stop clicking, it's marvelous. Well, that's all you're getting, folks. So, the first thing we learned, so in the first sort of 3 years of the project, what we learned was industry are really not doing a good job. Okay, so I won't go into detail about what this particular image is showing, but effectively, these are the 8 companies that joined us for the first 3 years. We got up to 11 in the second 3 years. But we had them looking at 3 different simulations. That was eventually expanded to 7, but this chart's easy to get your head around. And each one of these represents a different calibration device, or rather a characterization device, they've used to calibrate these 3 different systems. And what you'll notice is that across the 8 companies, there is absolutely no consistency. Every single company involved in this was using a completely different set of calibration tools and a completely different set of models to simulate the same three systems. So something is deeply rotten in industrial DEM. There is absolutely no consistency in what people are doing, and the odds of all of these different methods producing good results are pretty vanishingly small. So what do their results look like? So this is a super simple case. This is a rotating drum system. This is the ground truth data acquired using positron emission particle tracking. I would love to go on about what PET actually is. Don't have time today, but it's very reliable ground truth experimental data. And these are the 8 different attempts to simulate that one system by 8 different companies. And you have some that I would call are close but no cigar. Looks pretty similar, but there's a couple of key areas where its behavior differs from the real system. Then you have these that are a long way off, and then you have these that are actually physically impossible. Okay, so we have a diverse range of failures, but they were ultimately all failures. Now, the worrying things about this. Number one, all of these companies actually use DEM to model real systems that produce products that we use, eat, wash with, take as medicine. Wee bit scary to me. Number two is that obviously if you see that as a DEM engineer, you're going to realise that something's up. But if you looked at some of these ones, well, yes, if we can see the ground truth data, we can tell that it's wrong. But in industry, we don't tend to have PET, so that's kind of gone. So would you know that that is wrong if you didn't have the ground truth data staring you in the face? Probably not. Option 3 here is this is me being really, really fair to these companies, okay? This was the simplest possible case. This was some monodisperse MCC particles, dry, large, non-cohesive in a rotating drum. One of the easiest things one can possibly model. And they're still not being able to hit it. So imagine if you start introducing nasty aspherical cohesive particles, if you start introducing a second phase, etc., etc., etc. For a bit of audience interaction, you can set that down for 1 hour, and the concentration spans of this generation aren't what they used to be, which is in my generation. So I'm going to give you a little game to play. So hopefully when you scan this QR code, you should see a little discrete element method game of calibrate the rotating drum. So this is exactly the challenge that we set all of our industrial partners. And I'm just going to give you a couple of minutes to try and tweak the parameters and see if you can get agreement. I'll let you struggle with it for just a few more months.
That's just a quick question.
Please do. That's a great time to ask a question. Yes.
How much time and effort did the companies actually put into trying to do the benchmark calibration?
So what we did was, I know industry will know that that's a bad idea. So what we did is we did interviews with them to ask what methods they would undertake. Then my team actually did the slog and then interacted with them during the slog to get their opinions. So yes, the first time we did it, we did try to get industry to do it, and it failed abysmally because nobody did anything. So the next time we just said, right, what should we do, and we'll go away and do it for you, and it worked exceptionally. Very interesting. You work with industry, I assume.
Yeah, I could imagine them at 5 to 5 on a Friday going, oh, I've got to do this damn thing.
Yeah.
Oh, there's an answer. That looks okay.
Within the first year of the project, we got results back from the sum total of one person at one company. Yes. Okay.
Good result.
Indeed, indeed. So has anybody got perfect agreement? unsurprising. But and now the thing to think about this is that there's two all possible agreement. It's not bad, actually, is it?
Bad, yes,
It's not bad. Is it perfect? would you trust it?
Circles?
The point is, there's 2,352 combinations. When you're actually tuning a DEM simulation, you don't just have 5 choices of restitution coefficient. You don't just have 5 choices of friction coefficient. You've got a technically infinite number. Now imagine, instead of having to tap that button, each attempt takes 24 hours, at least, depending on what you're simulating, and we still can't guarantee that any of these is going to be correct. So the point is, for those who didn't already know this, JP at the back, certainly, it's a damned hard thing to do. And it's, even if you know what you're doing, it's still an extremely inefficient thing to do. So, by the end of the project, what did we come up with that does it better? What sort of set of rules did we come up with? And again, it's a part of a not particularly long talk, so I can't go into the full detail, but I will give you some of the headlines. I will give the disclaimer at this point, because I'm in the room with a lot of DEM experts here. I'm not saying this is the only way to calibrate DEM simulations. I'm also saying it is not necessarily a way that works for all DEM simulations, but it is one of the few that's been rigorously tested across a bunch of different systems. So what we came up with at the end of this project is a piece of software that we call Access, Autonomous Characterization and Calibration using Evolutionary Simulation. And the workflow is fairly straightforward. You decide what you're going to model. You choose some kind of a cost function to quantify the difference between the ground truth data and some real data, choose a suitable optimizer, and iterate towards the results. So for the project, and indeed this is the machine that we found to be the most useful for pretty much any free-flowing system, was the Granutools Granudrum. The reason we like it, it's got a very diverse phenomenology. It requires a relatively small number of particles, and it's very sensitive to most key DEM parameters. So sliding friction, rolling friction, cohesion, all have a very strong effect. And we also found that it's probably the only commercially available device that also showed a reasonable sensitivity to the restitution coefficient, which is kind of important if you want to model things like resonant acoustic mixing. Step 2, we've chosen our calibration system. We now want to define a cost function. And again, the way we build Access, you can pick your own cost function. You guys will get to play with Access tomorrow morning, so you'll learn a lot more about this. This is a very flying overview. But you can pick system velocity, you can pick velocity distribution, you can pick density distribution, granular temperature, anything you want. For the case I'm going to walk you through today, and that you should look through a little bit more tomorrow, we've got a free-flowing, simple powder, so we only really care about sliding and rolling friction. So we're going to take the free surface shape as our cost function. How do we actually make this into a cost function? Well, you can quite simply characterize it as a third-order polynomial, and then you can compare the polynomial you fixed for the top there, for the experiment, to the polynomial you fixed for the simulation. You can integrate the space between them, so your cost function becomes the integral of the absolute difference between these two polynomials, and then effectively that goes to 0. You know you've got perfect agreement between experiment and simulation. You've got, hopefully, a correctly calibrated simulation. Then comes the optimization step. I'm hoping for once I'm in a room where I don't need to go into great detail about evolutionary simulation. Hands up into the room if you're familiar with evolutionary optimization. Hands up. Okay, right. Hands up in the room if you're familiar with evolution. Okay, still not all the hands up. So, evolution was this marvelous thing discovered by Darwin. Okay, so you have a population of animals, you have a population of birds. Each of those has a fitness that you can quantify. So let's take the physicist's bird, a very simple animal. Its fitness is defined by how well it can fly. The ones that don't fly very well, fly into walls, they get eaten by predators, they're removed by the gene pool. The ones that fly excellently, they pass on their genes to the new generation, and the next generation is therefore a little bit better at flying, a little bit fitter than the last generation. I don't care about birds, but I do care far too much about rotating drums. So the principle that we use, we create an initial population, a generation, an epoch, whatever you want to call it, of different rotating drums with different randomly chosen DEM parameters. We then assess their fitness according to this metric that we've developed. We then kill off the ones that simply don't represent the ground truth data of the real system well. And then the ones that are very fit, the ones for which these lines are extremely close together, we pass their genes on to the next generation. The reason we like evolutionary algorithms for this is because they're very good at handling very non-convex, very non-smooth phase spaces. And this is what it looks like. So this is our evolutionary optimizer going through guess after guess after guess after guess. The white space is the disagreement between the experiment and the simulation. And as you see that guess after guess, generation after generation, it slowly iterates towards near perfect agreement. Very near perfect agreement. So this is, after optimization run, this is the experimental free surface profile, that's the simulated free surface profile. And the difference here is something like 4 millimeters squared across the entire surface of the drum, which is a pretty good percentile root mean square error. Now, those of you who are mathematically minded and or machine learning minded, you'll notice that a third order polynomial only has so many coefficients, which means you've only got so many closures for your relationship. What if I want to calibrate more than 3 parameters at once? Well, you can either use multiple different devices, or you can take multiple different measurements using the same system. As this talk is more about AI than it is about calibration, I won't labour this point. It's interesting to me because I'm a deep, deep calibration nerd, but not everybody necessarily is. If you have questions about it, very glad to answer them. The other thing that really came out of the IFPRI round robin, which is another thing that, one of the things they didn't realise, they didn't sort of, people who were calibrating in industry generally, not entirely, you're going to get a talk from somebody from industry in a couple of minutes who knows an awful lot about this, but they see it as more of an art than a science. So the idea that if I want to calibrate 3 parameters, I might need 3 data points to calibrate against was like magical new knowledge to them. Similarly, the concept that if I want to simulate a nice free-flowing system, I probably want to use a calibration device, a characterization device that is relatively free-flowing. But if I want to calibrate something that's dense, high stress, and under compression, I might want to use something more like a Schulze shear cell. It was also kind of a novel finding of the IFPRI project. So that's a flying overview of access and the IFPRI round robin. But while we were making this, what we realized is we had a very versatile modular workflow of this. Because when we wrote it, we were very careful to make sure that everything wasn't hard-coded in. If you don't want to use a granular drum, that's fantastic. Don't worry, use a shear cell. If you decide that CMAES is not the optimizer of choice, fine, plug something else in. If you want to use it with open foam instead of lights, fantastic, do that. So we've got a very open, very modular workflow. So the question arose, well, what if we opened it up further and didn't just use it for calibrating simulations? So that leads us on to the next part of the talk. Rather than just using optimization to optimize the parameters of the simulation, what if we wanted to use it to optimize the actual system that we're simulating? So to do this, we took a bunch of different open source tools and we tied them all together to make highly autonomous, rapid prototyping for particulate processes, which is now kind of a misnomer because we've now extended it even further and it doesn't just work for particulate processes, but I was really proud of the name and the logo, so we kind of just kept it. So we tie all these things together so that effectively we have a set of tools that we can use to programmatically define the geometry of a system. We can then programmatically create a simulation of that system, so we put in all the geometric bits here, we put in all the particle properties and system properties here. We then parallelize it so we can run a bunch of simulations, and we then do the analysis and the optimization in a loop up here. And then we go all the way around back to the bottom. The thing I find myself having to say more often than I would have expected is this is all entirely autonomous. I don't have one of my PhD students just sat there clicking buttons endlessly for several weeks while this runs. And crucially, you know, it can be run using any simulation software. So we're talking DEM here, so I've got lamps and lights as examples, but you can stick MPPIC in there, you can stick CFD in there, you can stick molecular dynamics in there, you can rip any single part of this workflow out and relatively easy wang something else in its stead, and that's the way I like it. So it's always very hard to describe in an engaging manner by talking you through it in a very abstract way. So let's talk through a specific industry relevant example. And the one I'm going to go through at length here is milling. I like milling because a big focus in my research group, other than artificial intelligence, is sustainability. Okay? And mills are a fantastic system to work on if you're interested in sustainability, because they use, depending on the estimate you're reading, somewhere between 3 and 4% of all the electrical energy that we produce as a society. And a typical mill is somewhere between 0.1 and 15% efficient. So if you can improve this process even just a little bit, and you can convince these improvements to be adopted on a large scale, you stand to do a massive, massive, massive benefit to the environment. Now, the industries that I work with, so this was actually came out of a project with Mondelez. This was about cocoa milling, so producing chocolate. Their mill uses 35% of all the electricity in their factory. Okay, just again to put it into context. But they haven't really done much to improve this mill because trying to improve it via trial and error experimentally is simply beyond their financial resources to do. So how can we do this in a more tractable manner? Well, spoiler alert, kind of doing what we've just talked about before. But this time, instead of our variables being restitution coefficient, friction coefficient, cohesion, blah, 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 we now try and deconstruct the geometry of our system into bite-sized chunks so that we can optimize different aspects of that. So for an attrition mill, they're pleasingly simple systems. So we can vary things like the length of the pins, the thickness of the pins, the number of pins, the angle between the pins, etc., etc., etc. And then we set a goal. And the goal is the crucial point here. Our goal is to reduce the energy use of this mill. Okay? That was the big problem. It was giving them lovely, you know, you've all eaten Cadbury's chocolate, right? So there's nothing wrong with the chocolate, the quality's fine, but why can't we make it slightly more energy efficient to produce? So, again, back to the birds, but this time I'm not interested in birds or rotating drums, I'm interested in mills, so we do the same thing. We produce an initial population of different mills with different randomly chosen designs. We assess the fitness, which in this case, the fitness is a very simple metric. How much power does it use? Lower power draw, higher fitness. And then we kill off the ones that aren't very fit, the ones that use a lot of energy, and we go around the process again and again and again. So let's see how it does. This is each slide that we're looking at here is one generation of the evolution. Oh dear, doesn't look like a very good mill. Can anybody give me an idea of what went wrong? Yes.
It's not milling, so it's not using much power.
Precisely. So the short, nothing went wrong, right?
needs to set up the kinetic energy between each grinding beats by minimizing optimization.
So the correct answer to this is actually nothing went wrong. It did a fantastic job of doing exactly what we told it to do, because that design, the rotating stick, is incredibly, incredibly low power draw, but it's not a very good mill. So as Carsten rightly intoned, what we need to do is actually have a second aspect to our objective function. So in this case, we said, right, objective 1 is to minimize power draw, but objective 2 is to maintain a minimum mean pair stress energy between the colliding beats. And it's still pretty simple. You can just put that in as a set function. Anything where you're not getting enough stress energy, it's got an effectively infinite cost function, get rid of it. Anything where it's producing enough energy, let's judge it on how much power draw it produces. So when we go through round 2, all of a sudden, we start to see some slightly more intelligent looking designs. And if I was to run this video the whole way through, what you'd find is it starts to converge on a family of designs with some relatively similar properties. So the designs that it eventually came up with had energy savings of between 24% and 40%, which, while not extravagant, if you're talking about something that's using 35% of a factory's entire energy costs, is pretty significant. So I work with Mondelez's sustainability team, and they reckon that if they can implement this across their entire site, it will save them about £200,000 a year, and it will save them about 500 tons of CO2 per year. Okay, which is quite powerful. The other interesting thing, as I say, is that a lot of the top performing results shared certain features, which suggest that the algorithm, simple as it may be, has learnt, if you will, what makes a good mill. And what we found of what it was with a typical attrition, you've just basically got something like that, cross, cross. Pretty boring, pretty simple. What this seems to have done is you've got lots of long, relatively thin, staggered pins, and what that does is, because they're staggered, you have particles leaving one pin, rather than just ploughing a furrow until the next pin comes around, it's immediately whacked by another pin. So you've got an element of chaos. You're increasing the number of collisions per rotation, which makes it a more efficient mill. So that was really interesting. And like so much of the stuff that we see designed by these evolutionary algorithms, it shows us something about the optimal design, which retrospectively is really obvious. Okay, stagger the pins, create more chaos, that's going to give you better milling. Yet, in the several hundred years that people have been performing milling, no one ever seems to have come up with that specific design. So, it's a nice example, but it's a relatively dull one, because all you've got is pin thicker, pin thinner, pin longer, change the angle. What if we've got something with a slightly more complex geometry? What if I'm not interested in mills? What if I'm not interested in particles? What if I am interested in particles, but I've got to have some gas or some fluid in there as well? So we've actually applied this to a range of different systems. So this one here was the work we did with Unilever. This is their quote-unquote mixer. I call it quote-unquote because it's in its base incarnation here, it didn't really do much mixing. So this is producing soap. I was very disappointed to learn it's not actually Dove. So it's some vague soap they only market in India. So I will never feel the fruits of my labour here, which is a shame. But this is their original design. This is our optimized design. And compared to the rather decent results that we achieved with the mill, the results here were really, 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 really striking. If you look at the difference in the rate of mixing, it was a tenfold improvement in the mixing rate. So if you look at it from the point of view of someone who's interested in sustainability, that's a 90% reduction in your running costs. And so it's a 90% lower energy cost, but it's also 90% fewer CO2 emissions. So you're kind of doing the holy grail here, which is doing something that's both more sustainable, but at the same time more profitable. which is kind of kind of my goal in life. We've done work with fluidized bed reactors. We've done work with wind turbines, and the wind turbines are a really nice example. And I'll step through this one a little bit more slowly because the DEM mill was one of the first projects we did, and it was a bit clunky and a bit simple. We've got a lot more elegant now, as you can probably see when we're talking about the wind turbines. So we have developed a novel mathematical parameterization that can describe any wind turbine in existence. You'll notice I deliberately blurred this because our central IP team want us to patent it, and they've asked that I don't let anybody see the math. So there is some maths there, but I've kind of Epstein filed it a little bit. But it can produce any existing vertical axis wind turbine just by tweaking some of the parameters that we include. So just by changing one of 24 different coefficients, you can make a Darius, you can make a helical, you can make an H-rotor, you can make a Savonius, you can make a solar wind, you can make a Protectus, all from a single mathematical model. All very impressive, but the crucial point here, the really exciting thing about this, is that it can also produce an effectively infinite number of wind turbines that have never existed. Okay, so we create a geometry, and then we go through the same rigmarole. So we then stick that geometry into a CFD simulation. So this is a specific rooftop in Edinburgh, actually. And the reason we did one in for Birmingham, we did one for Edinburgh. And the power of this is that you can make the ideal design for a wind turbine for a specific topography, for a specific set of wind speeds. So you can get these things working in areas that they've never worked before. So make some windmills. This time our fitness is the conversion of wind energy into electrical energy, kill the ones that don't look much like wind turbines. And the end result, so this was the one that we designed for Birmingham. This was what we call the Birmingham Blade. And this got us on the local news because this fellow, David Kumar, he'd done an article about wind turbines in Birmingham a few years before. The summary of which is they don't work in Birmingham because we don't have any wind. Okay, there they are. They're the existing wind turbines not working despite the fact that there is some wind. And the point is, so wind turbines don't really work in Birmingham unless you design them specifically for Birmingham. So another nice application of AI. So I have got a few minutes left, so I'm going to go a little bit provocative here because I've done it's a DEM meeting, but it's also an AI meeting. And I think that the majority of people in here, at least judging by the evolutionary algorithm question, skew more towards the DEM side than to the AI side. Am I right? Lots of nods. Okay, so I thought it might be useful to opine a little bit on the good use of AI in simulation. So in the research group, so I've talked you through two examples. We do a lot of other AI stuff, and there's sort of a common thread in the tools that we most commonly use. Anybody notice the common thread in the tools that we typically use? And I will preface this by being, don't be afraid to sound like you're being rude to me. They're all pretty old school. Okay, the favourite AI ML tools that I use most broadly are pretty old school. And that's not because my students aren't very good, I promise you they're excellent. It's because there is sometimes an advantage to not necessarily using the latest, most cutting edge thing, okay? When I was doing my work as an independent scientific advisor for Bridge AI, one of the things I found as I went around and I talked to lots and lots and lots and lots of different AI companies was that there was this kind of misconception that to be innovative meant I have to use the newest AI. If I'm not using a large language model, I am failing at life and I'm not an AI company. But innovation and recency are two very different things. Okay, and I think that's an important thing for those of you who are getting onto the AI bandwagon. Realize it doesn't have to be ChatGPT 5.2 to be innovative. because a lot of the older AI models that we use in my research group were actually created in a time where you could not dream of the amount of computational power that we have, or the simulation capability that we have, or the simulation models that we have. So there is a lot of value being missed by not going back to the stuff that was invented in the bad old days when we were talking about RAM in megabytes, okay, and towards dragging it into the model. Crucially, it's also a heck of a lot of these older models are what I would call much more lightweight. They are a lot more computationally efficient to do extremely similar jobs. So by going for the old school as opposed to the next big thing, you could potentially do the same job faster, almost certainly more sustainably, but also quite possibly a little bit better. Okay? The second thing to mention, again, for those of you who are going to go and work with industry, the industry mindset and the academic mindset are, I was going to say subtly different, but I think what I actually mean is bloody different. They're not always after the most modern thing. Because the problem with the most modern thing is it's not necessarily trustworthy, okay? Especially so with AI, because the bigger and more complex the model, the more black boxy it is, okay? And for reasons that I can't fully understand, I did once give a talk on artificial intelligence to the rail CTOs of Europe, which was, do not ask how I got roped into that. And I talked them through some of the details of the different AI methods, and I asked them who would use a neural net to be in charge of safety on the railways, and nobody in the room put their hand up. Because industry folks, especially where you've got safety critical systems, are very nervous about something that they can't see the cogs moving. And of course there's a whole research field trying to make AI models more interpretable, but in the short term, industry can be a little bit skew-whiff about it. Sustainability is a really interesting one. So these are the CO2 emissions in metric tons. These are your emissions if you drive a typical petrol-fueled car for a year. That's what it took to train GPT-3. That's what it took to take Llama 3.1. I think they've actually stopped releasing data on this because as you can see the start of an exponential increase here. So I dread to think what GPT-5 looks like on this graph. Now, the other big problem with using the big models is the reliance on training data. One of the really powerful things about things like PySR that you were talking about, or like CMAES that we use in Access and HARP, is you can fit a pretty damn good model with a few hundred, maybe even a few dozen data points. If you want to train a transformer model, or if you want to train a deep neural network, you need a lot more than that. And if there is one thing that I have found, there are very few things common to all the different industrial sectors, but one of them seems to be that large sums of extremely clean, well-organized data is not something that they tend to have. So if you can use a more lightweight model, it can be really, really valuable because it might just be able to cope with the dirty, sparse data that companies do have, or if not, then maybe you can create your own data using DEM and not have to use the entire runtime of Arch 3. The other reason I really do like my evolutionary algorithms and my reinforcement learning as opposed to the great big data-driven models is that they have a fantastic ability to think outside the box. So when I show the example, the Unilever example, with the 1000% increase in throughput, I often get a lot of odd looks. Well, why hasn't anybody come up with that before? And the short answer is because it's always been designed by humans. And the problem with a data-driven model, especially if you're looking at industrial optimization or stuff like that, if you train it on past data, it is going to inherit the innate biases of the past data. It is going to learn all of the human constructed design laws that we've put in there. And oftentimes, if you've ever spoken to an original equipment manufacturer of some kind of a mill or a mixer, I remember I had a fantastic conversation. I think Anthony will remember We had some great conversations once at Paltech about this, where there was this one equipment manufacturer. So why do you design your mill like that? Well, because that's how we've always done it. Okay, but why specifically this design? Well, that's how we've always done it. And that conversation just kept going on for about 5 minutes until we gave up. Okay, and you train your model on that data, it's going to inherit it. Whereas if you start with a completely random Gaussian distribution, it's not picking up that bias. Okay, so you can really think out of the box. And rather than eking out 5–10% increases in performance, occasionally you will get the 1000%. The final thing is going back to that graph, Llama, ChatGPT training. That is the CO2 cost of all the work we have ever done with HARP. So everything we've shown you today, and probably another 200% on top of that, that's how much CO2 we produce doing it. Okay? And that's how much CO2 we can save with a single project. So, I mean, that's the thing I'd like to leave you with. You know, AI, and don't get me wrong, I'm not a Luddite. I don't hate large language models. I don't hate agentic AI. I think all of these have a time and a place. But what you do tend to see with new adopters of AI these days is they will jump from absolutely nothing to a transformer model and just leapfrog everything that comes in between. Okay? If you've got an awareness of what comes in between, you might find that you have something faster, more efficient, and potentially also at the same time better than jumping straight to the most modern, most shiny, most fancy tool. So that's all I've got to say now. I'm aware it was a tremendously flying overview of quite a lot of technology. That is because Leonard, my former student, is going to give you a much, much deeper dive on access and also some of the symbolic regression work that we do that I didn't have time to talk about tomorrow. If you do have any questions for now, I'm very happy to answer them.
How many parameters do I need to describe a vertical axis wind turbine?
So a vertical axis wind turbine, I think it was 23. It's a lot of parameters, but what you'll find is when we work with most companies, the 23 parameters is the model that can describe literally any wind turbine that has ever existed. When you actually work with industry, what you can do is you can start to put constraints in it. Well, I don't want it to look like that. Okay, let's switch off those 3 parameters. And also it's got to, you know, I don't want to have vanes because they'll look ugly on top of my building. Okay, let's stick off these 3 parameters. So by the time we actually get it working with industry, it's probably closer to 10 or 14 because not everybody most of them have an idea of what they want to do.
Can I ask one, actually, if I can interject? So it occurred to me when you were talking about the mill and about the wind turbine, is there any consideration of manufacturability?
Brilliant question.
Because they look more expensive, basically. And we saw it as well in the example Carsten showed us in Formula One.
Yeah.
Basically, that front wings become ever more complex and expensive to manufacture. Does that feature?
So the short answer is it can do. So it's what we tend to do when we're applying these things is we start off with a sit-down meeting with the company we're working with, and we talk about, right, what are you capable of manufacturing? How important is being able to clean it easily to you? And what you can then do, you can either A, put in a set of constraints so you can stop it ever even trying these things, or alternatively you can apply it as a penalty. So you can sort of say, right, so it can give you something that's very difficult to clean, but only if it's significantly more energy efficient than the base model. So any of these things can be programmed in as either a constraint or a penalty, or indeed as part of the fundamental kernel. Really good question.
Excellent. Stefanos, then JP.
I'm no AI expert, but I think that your comparison of CO2 cost or the sustainability aspect is not exactly fair because essentially GPT and similar tools are pre-trained. And to me it's interesting because you said, for example, at some point earlier on when you were showing the mill, that the system learned something and then that learning disappears, because the next time you're optimizing something, you don't have that learning. So to me, the question is, how can you store, how you can pre-train and store all the learning so that next time you try to optimize something, you are able to use this knowledge. Because, you know, as you said, when you had the people designing it, oh, that's the way we've always done it, but that was very efficient for the capability of the time, because you had stored in the people and in the documents the knowledge. You didn't have to start from kind of reinventing the wheel every time. So how can you avoid that? Still, yeah, keep the low-cost models, but provide them with, you know, with ready food, with ready knowledge, essentially, so that they don't have to reinvent from scratch.
Yeah, this is a really good question. I'm aware it's an imperfect comparison, but it's very hard. That's the only data that I could find in a reputable journal. So there's various ways you can do that, and it is a really, really interesting question. The first and simplest, if we're talking about you know, the same system and optimizing it over and over again, as it were, we do save all the parameters of all the simulations that we've made, so that we can just restart it at the same point, or restart it at epoch 5, and it will have those previous runs still stored in it. You can start from the sort of more narrowed down distribution, as an example. That's one way of doing it. The other way of doing it is this is much more human and much less AI here, is once you've run a couple of simulations, what you learn very quickly is that some of the parameters don't need to be there, so that can be learned. So you can actually take a look at what it throws away and use that as a way to learn, to improve the next run and make it more efficient. But I think one thing I failed to say, which is the point of what we're doing here, the whole value of it is to create tailored geometries, if you see what I mean. So a wind turbine for specifically this part of Birmingham, or a mill specifically for cocoa liquor, or all the rest of it. That's the reason we're able to get these particularly strong increases in efficiency, is because the idea is to eventually move away from mass-produced generic pieces of equipment, and actually, you know, a mill made by Cargill or whatever, or Gear, whatever, is going to be a jack of all trades, because they're going to sell that mill to pharmaceutical people, they're going to sell it to chemical people, they're going to sell it to food people, and they want it to work very well with all of those different ones. The idea is, if you've got a tool like this, to be able to optimize the design for an individual company and an individual product within that company, because that's the only way you can get these really maxed out efficiencies. So to an extent, you do need to start from scratch a little bit each time, and that's kind of part of the point. Very good question.
A long question and a long answer. I promised 2 other questions and answers, so JP, make it quick.
Okay.
Sorry.
Okay, so when you talked about calibration, one of the nice conclusions was right tool, right job kind of thing. You know, no clear system, know what to do. It seems when it comes to DEM and AI, we're nowhere near being able to define right tool, right job. So if we're trying to do a temporal system, or if we're trying to look at a stress-defying system, even when Carson was going through his talk, mentioned it a few times where, you know, I wouldn't do it this way now because human intelligence has learned something, better ways of doing it. So how far away from how far away are we from being able to write down a list of, if I want to predict mixing over time, I use this method. If I want to predict tableting, which is kind of static, and over time use this method. It's, you know, these guidelines on usage, we're still learning, obviously, but have we kind of made progress in saying, don't do this at all, ever?
So, interestingly, my answer to that would probably be very different to my answer for characterization devices, because a single characterization device is limited in its output. If it is a high-stress characterization device like a shear cell, it can only give you information about a high-stress system. Now, the AI tools that Carsten was talking about, they should, hypothetically, be much more generalizable. So my hope would be that the physics of DEM is actually pretty damn simple. So my hope would be that actually there should be one tool that can do it all. That would be my view on it, because their calibration and emulation are two wildly different concepts. And I think you probably, with enough time and patience, you probably could already find a universal emulator, because the AI doesn't have the same constraints and limitations that a real physical characterization device does.
So, final question from Chris.
And I'm also saying when I was thinking about this comparison of the car and the large language model and your system, and also about is this a fair comparison? And then what would be a fair comparison? Is it a fair comparison if we don't take only the training, but also all the usage energy of all people, and all these people are working then on CO2 efficient processes? Would that be a fair comparison?
So I came to the conclusion a while ago that I don't think there exists a fair comparison, because the reason I wanted to give the most conservative comparison I could, because unfortunately there are a few more users of ChatGPT than there are of my software. So it would be an unfair bias. So I think to call it a comparison is innately unfair, I think, really, because there isn't a fair comparison between these two different things. But what I wanted it to be was indicative, that that just to train this particular model once is using 50 times more energy than everything I've ever done in my laboratory with this, and that each one of those things that I've done in my laboratory is saving about 100 times the energy that we used to train it, that it's a decently sustainable thing to do. Yeah, it's the best effort. Okay.
Fantastic. So let's thank Kate again. We're now on a break for the next 25 or so minutes until 20 past. There was planking outside, so there is tea and coffee.
There's fresh tea and coffee here, and the old tea and coffee is still there.
Wonderful.